Okay, hello everyone. Welcome back. Before we can really begin to do calculations with entropy, we need a few more definitions and a few more relationships or surrounding entropy. And so in this video, I hope to define those relationships and give you a summary of some of the equations that we are going to be using throughout this chapter. Okay, so the entropy change of the system is going to be given by this reaction. Oh, and we got a typo here. This should be N. And so this is where the delta H of the reaction is going to be equal to the inherent entropy of the products minus the inherent entropy of the reactants. So this is really very similar to what we worked with in chapter 6 with Hess's law and enthalpy, where we got these values from a table. And these n's are the stoichiometric coefficients. And then we added things up and we found this delta of the reaction. And in this case, this is the delta S, so the change in entropy for that reaction. So we can, without doing calculations, we can make some predictions on if we expect the entropy to be greater than 0 or less than 0. And I should say the change in entropy. And so one way is by looking at the reaction and saying if the moles of gas increase, then the change in entropy of that reaction should be greater than 0. And so this would be something like water gas breaking up and forming H2 gas plus O2 gas. And now I need to balance this. And so I started with 2 moles of gas on as the reactants, and I went to 3 moles of gases on the products. And I'm just using the stoichiometric coefficients to figure that out. And so since I increased my number of moles of gas, I would expect that the delta S of this reaction should be greater than 0 because I'm increasing the amount of entropy within the system. And likewise, if it goes the other way, then the entropy should be decreasing. Okay, other sorts of predictions that can happen are things like if the products are less constrained, so taking something that is a ring structure, H, H, H. So something that is very confined and not able to move a lot, and breaking this up so that you then have a chain structure. So something like this, you would expect the entropy to increase. And if you were going the other direction, you would expect the entropy to decrease. These sorts of things are very hard to predict. I do not expect that these are things that your lecture instructors are really going to expect that you are able to do a lot of prediction with. But follow their lead based on what they've told you in lecture. So remember that we talked about how the change of entropy of the universe is equal to the change of entropy of the system plus the change of entropy of the surroundings. And we defined that the change of entropy of the system is equal to this products minus the reactants multiplied by their stoichiometric coefficients added together. We also need to define the change of entropy of the surroundings. And the change of entropy of the surroundings is defined as the negative delta H enthalpy of the system divided by the temperature. And so this is a definition. So endothermic reactions have, so now that we know the relationship that delta S of the surroundings is equal to negative delta H of the system divided by T, we can say some specific things about different types of reactions. So in endothermic reactions, delta S of the system is less than 0, which means that delta, or negative, which means that delta S of the surroundings is going to be positive because a negative times a negative is a positive. For exothermic reactions, the delta H of the system is going to be a positive value, and that leads to delta S of the surroundings being a negative value. Okay, I hope this summary helped to put all of these equations together all at once. Don't worry, we're going to start using them, and this stuff will start becoming a little more familiar to you. And keep in some of the next videos, I'm going to walk through some examples so that you are certain to see how all of this stuff comes into play.